Hello class, welcome to section 4.4. Today we're going to look at indeterminate forms and Hopital's rule. This is day 1 of 2 of our notes on Hopital's rule. So what are indeterminate forms? Indeterminate forms are forms like 0 over 0. The reason we consider this indeterminate is in the past you've been told any number divided by 0 was an error, right? You couldn't do it. Can't divide by 0. On the other hand, though, you had any 0 divided by any number was equal to 0. So which rule wins out here? Is it an error or is the answer 0? We aren't sure. We can't determine it. That is why we consider it indeterminate. The other one is if we have infinity over infinity. Okay. In the past, if you would have some number divided by infinity, like 1 divided by infinity, that would get really, really, really close to 0, right? If you take a small number divided by a very, very big number, we would consider it to be 0. On the other hand, though, if I had infinity divided by number, if I have infinity divided by 2, it's still going to be an extremely large number. It's still going to infinity. So who wins out here? These are our main 2 indeterminate forms. Okay, these are like our little goal to get to today. But there are a few other ones. We got 0 times infinity. This one was you were always told 0 times any number is 0. However, if you take a really big number times infinity times any number, it should still be infinity. So is the answer 0 or is it infinity? So this is another form of an indeterminate. Infinity minus infinity, that's another indeterminate form. 0 to the 0 power, that's indeterminate. Infinity to the 0 power, that is indeterminate. And 1 to the infinity, that is an indeterminate form. So these are all our indeterminate forms. We're going to focus primarily on these 2 today, and we're going to touch on these. And then in our next set of notes, we'll look at the ones with the exponents. Okay. So example 1 we got here. Our first idea whenever we're finding limits is always try and plug it in. Okay. So I'm going to try and plug it in. I would have ln of 1 all over 1 minus 1. This gives me natural log of 1 is 0 over 0. Okay. So this is an indeterminate form. So if I would have this, I would try and figure out, well, can I simplify this somehow, some way? Things that we've used to simplify find limits in the past was factoring, conjugate, if you could simplify in some way, shape, or form. If you have multiple fractions, get a common denominator, that kind of stuff. We don't have any of those options here. So this is where Hopital's rule comes in, okay? The way the rule works, if you have 0 over 0, you take the derivative of the numerator and the derivative of the denominator. You never use quotient rule. Never use quotient rule with the whole fraction, okay? But you take the derivative of the top, take the derivative of the bottom, and then you see if you can find the limit. So we go like this. We're going to use Hopital's rule. I make a little note. I like to write LHOP so that I know. You can write LH if you want, but every time you use this rule, you write LHOP or LH, okay? So we are going to use the rule. We are still finding our limit. So we have limit as x approaches 1, and then the derivative of ln of x is 1 over x all over. When I take the derivative of 1 minus x, remember we're doing them separately. Derivative of the top is this. Then I look at the bottom, take the derivative of that. It's just 1. Okay, now once you do this, I go ahead and I try and plug in my limit. I try and plug in 1. I would have 1 over 1. Can I do this? Yes, I can. And so my answer is just 1. Okay, so that's how Hopital's rule works. But the biggest thing is it has to be this form 0 over 0. It also needs to be the form infinity over infinity. Okay, so in order to use the rule, got to be these 2 types of forms. So, what does the rule state? F and G are differentiable, and the fact that G cannot equal, the derivative of G can't be 0 on an open interval, says, okay, that the limit as x approaches a of f of x equals 0, and if g of x equals 0, you'd have 0 over 0 in this case, okay? Or, if you get infinity, positive or negative infinity, then you would go ahead and have infinity over infinity. So if you have either one of these forms, you can use the rule. Going back to this statement, why can the derivative of g not be 0? Okay, see how g is in the denominator? So since it's in the denominator, you cannot have 0 in the denominator. Some things to recall or remember. If I have 1 over an infinity, okay, what does this get close to? 1 divided by a really, really big number is 0. Okay, so remember that this is true, or if it's just any number over infinity, that'd be helpful today. The other thing to keep in mind is if you have 1 over 0. If I have a 0, 1 over 0, that means there's an asymptote. So this is a form of infinity because you can't divide by 0, so there's an asymptote occurring. Okay, so remember those two pieces of information as we go throughout today. Okay, so try it again. Calculate. We got the limit as x goes to infinity, e to the x over x squared. So first things first, we always try and plug it in. Excuse me. This one you might need to think about graphically. What does e to the x look like? Here's what e to the x looks like. And as x goes to infinity, my y values are going to infinity. So this gives me infinity. X squared, if I were to graph x squared, I would have something that looks like this. And as that goes to infinity, as my x goes to infinity, getting large, my y values are going to continue to get large, so that's going to infinity. So this is the form infinity over infinity. Since I have this form, I can go ahead and use Hopital's rule. So I'm going to make a little note. I like to write LHOP, but if you want to write it like that, you can. LH. Okay. So the limit as x approaches infinity, the derivative of e to the x is e to the x. Then I take the derivative of x squared, 2x. After you take your derivative and simplify, this one doesn't have any simplify, you always try and plug it in again. Okay. So in this case, if I were to plug it in, e to the infinity would just continue to be infinity. And then 2 times infinity. Okay, that would be infinity as well. If you're not sure, what I would say is graph. What does 2x look like? It's a line with the slope of 2. So as you go to the right, it's going to continue to go to infinity. So once again, I have infinity over infinity. So I'm going to go ahead and use the Hopital's rule one more time. And the reason I know it's only going to be one more time is what's the derivative of the denominator going to be? It'll be just 2. Okay. So we got LH, little L hop. We're going to hop. So we got our limit as x goes to infinity. Derivative of our top is e to the x. The derivative of our bottom is 2. And now when I go ahead and plug it in, I'd have infinity divided by 2. If you take an extremely large number and divide it by 2, it's still going to be an extremely large number. So that would be an answer of infinity. All right. There is example 2. Example 3. Okay. Going to infinity again, I would think about what ln of x looks like. ln of x, remember, it's our pal, natural log. He looks like this. There is an asymptote happening right here, okay, at x equals 0. And then I would have this point right here on my graph, 1, 0. So as we go to infinity with ln, it's going to continue to go up. So this is infinity over, now the cubed root of x. Okay, cubed root of x, if you're not sure what that one looks like, you could graph it on your calculator. If you graph it, you'll see it has this shape. And as x goes to infinity, what's happening to my y values? They're going to continue to go up and up and up. So we are in the form infinity over infinity. Okay. So since I have that form, infinity over infinity, or if I were to have 0 over 0, I can LHOP. We're going to use the Hopital's rule. So we got our limit as x approaches infinity. Derivative of ln of x, 1 over x. All over, now I got to take the derivative of this piece. Remember, x, the cubed root of x is x to the 1/3. So I'm going to take the derivative of that. So it's 1/3 x to the negative 2/3. Now in this case, there's a lot of stuff going on. I have fractions within fractions. So if you ever have that, we should simplify before we go ahead and plug in. So I'm going to simplify. I still haven't taken my limit, so technically you guys should continue to write your limit sign. but this would be 1 over 3x to the positive 2/3 if I move that 2/3 down. And then I would go ahead, flip and multiply. So times 3x to 2/3. All over 1. Those all cancel out. I have my limit as x approaches infinity. I have 3 in the top. And then I would have x, if I combine this is x to 2/3 and this is x to the first. Bring the 2/3 down to the 1 and subtract, so it would be x to the 1/3. And now I would try and plug it in. So I'd have 3 over, plug in my infinity to the 1/3. Well, that's this graph here. As you go to the right, what's happening to my y values? Continue to go up. If I have 3 divided by a really large number, I will have 0. Okay. So there is example 3. Example 4, your favorite, trig functions. Okay, so what we're going to do, I would use your solo yellow sheet to help you out. We always try and plug it in. So tangent of 0 minus 0 all over 0 to the 3rd. To figure out tangent of 0 is sine of 0 all over cosine of 0 minus 0. 0 cubed is 0, so I have that. And then sine of 0 and cosine of 0 on my unit circle. I would go ahead and look right here. This is where my radian measure is 0, and my ordered pair is 1, 0. Ordered pairs are cosine, sine, so it's 0 over 1. So I have 0 over 1 minus 0 all over 0. Well, 0 divided by 1 is 0, so this gives me a form of 0 over 0. Okay, so since I have 0 over 0, now I can go ahead and use the Hopital's rule. So I'm going to LHOP. Limit as x approaches 0. Derivative tangent. Secant squared of x, that's on your solar yellow sheet, minus 1 all over 3x squared. Now what I would do is I would go ahead and plug in 0. I got to find secant as 0. Okay, so I'm going to make a little note. How do we find secant as 0? It's really 1 over, secant is 1 over cosine of 0 squared. So I'd find 1 over cosine. My cosine is 1, so I'd have 1 over 1, and then I'd square it. Okay, so I'd have 1. So this gives me 1 minus 1, which is 0. All over, I plug in 0 here, and I get 0. So I have 0 over 0 again. So I must go ahead. Now that I have 0, 0, I use LHOP's rule. And I take the derivative of the top, and I take the derivative of the bottom. Okay, in order to take the derivative of my top, though, secant squared is really secant of x squared. So how do I find the derivative of that? It's our pile the chain rule. The outside is x squared, and the inside is secant of x. This is 2x, and the derivative of secant you can find on your sheet, but it's secant, secant tangent. Then you go ahead, take this, plug it in here, and multiply across. So I would have secant times secant, so secant squared of x times tangent of x. That's the derivative of my top. 2 secant squared of x tangent of x. And then I would say minus the derivative of 1, which is 0. Okay. All over 6x, not squared, just 6x. Now I would go ahead, plug in 0. I already know that if I plug in 0 to my tangent piece, if I just look right here, what did I get for that piece? I got an answer of 0. So this part right here is 0. And then my secant squared, what did I get for secant squared? I got 1. Because I already found that earlier, right? Secant squared when I plugged in 0. So what I would notice is this would be 2 times 1 times 0 all over 0. So it's going to give me 0 over 0. And what I could do is this would be a product with a chain rule. Okay, it's really 2 secant squared times tangent. But in order to, I'd have to product, and then I have to do the chain rule of secant squared. I would notice this would be the last time I'd have to do the rule, because what would the bottom become? It'll just become 6. So I know I'm not going to have an LHOP again. But there's actually an easier way to handle this. What I would do is separate it. I'm going to pull it apart. Do you see how secant squared is 1? I'm going to take the 2, the secant squared of x, and just the 6, and I'm going to say I want to look at this limit. Times, what do I have left? My limit as x approaches 0 of tangent of x all over x. If I didn't notice I could do this, you'd be able to do the product with the chain rule, and you would be doing just fine. You'd be able to get the right answer. It's just that it'll save you some time. So if you notice like it's going to get more complicated rules, can you separate it so you could find one part of the limit, so you don't have to continue to do complicated derivatives? Okay. So let's just find this part right here. As I plug in 0, we already know secant squared of 0 is 1. So I'd really have 2 times 1 all over 6 times my limit as x approaches 0 of tangent of x all over x. Okay. If I plug in 0 to tangent, we already know we get 0. And if I plug in 0 here, I get 0. So this is a form of 0 over 0. So on this limit here, I'm going to LHOP. So I have 2 over 6, which is 1/3, times, and I'm LHOPing from here to here. LHOP. My limit as x goes to infinity, sorry, x goes to 0. Derivative tangent is secant squared of x all over 1. And now I can plug in 0. We already know what secant squared of 0 is. Where is it? Right here. Secant squared of 0 is 1. So I have 1/3 times 1. And so my final answer is 1/3. So example 4 is one of the more complicated ones that we're going to cover today. But there is example 4. Example 5, we always go ahead and plug it in. I see we're going to pi. So on my unit circle here is pi. This is the ordered pair, -1, 0. So sine at pi is 0 all over 1 minus my cosine value at pi, -1. This gives me 0 over 2. What is 0 over 2? I can do that. So always don't forget, you guys, not every single time you're going to have to use the rule. Here you wouldn't be able to. You have 0 over a number. You can take 0 divided by 2. It is 0. Okay, so there we did not even need to use the rule. Then we're going to look at the last 2 type of indeterminate forms for today, and then tomorrow we'll do the ones with infinities, or sorry, not infinities, exponents. So we can have indeterminate forms like 0 times infinity or infinity minus infinity. Typically, in order to handle this form, you rewrite by moving monomials. Typically, this is not always, but monomials to the denominator. So for instance, and I don't know if what this would give us off the top of our head, but if I have x to the third times e to the x, okay, you could take this and rewrite it, and I would have e to the x all over x to the, if I move something from the numerator to the denominator, I change my sign to a negative. So it's kind of typically how we handle this type of situation. Okay. If I have subtraction, typically how we handle this one is, if I have something being subtracted, I will rewrite it by making it one fraction. So rewrite by making one fraction. And the way you guys get one fraction when you're subtracting things is you get a common denominator. Okay, so we're going to go ahead and look at these forms, but those are typically how we handle those. All right, so we're evaluating x times ln of x as you approach x as the x approaches 0 from the right. So for this one, I would plug in 0 for x, and I get 0. Now, ln of x, remember, looks like this. This is the second time I've graphed it today. At least the second. Maybe more, I don't know. For sure, 2. Here's ln. There's my asymptote. So as you approach 0 from the right, this is your left hand, this is your right hand. So here's my right hand limit. I'm approaching, and as I get closer to 0, it's going to continue to go down and down and down. So this is really 0 times negative infinity, which is our 0 times infinity form. So when we have this case, we go ahead and try and rewrite by moving somebody to the denominator. So I'm going to take my x and move it to the denominator. So I have my limit as x approaches 0 from the right, and I have ln of x, and I'm going to bring the x down, so now it's x to the negative 1. Now if I plug in 0, okay, we know that this is 0, and here, this piece we need to look at. I'm going to come over here and look at it. X to the negative 1, I can think about it as 1 over x. If I plug in 0 here, I would have 1 over 0. What did we discuss earlier about 1 over 0? It's a form of infinity. Okay, so we have infinity here. I hope I didn't write 0. I didn't say 0, did I? Did I talk about this right? Oh my. Okay, let's backtrack for a second. So ln of x as you approach 0 from the right, that's going to negative infinity. The bottom piece, I can rewrite it as 1 over x. Then if I plug in 0, I'd have 1 over 0, which is a form of infinity. Okay, because there's an asymptote there. The other thing you could do is you could graph this function on your calculator. And it looks like there's an asymptote there, but it looks like this. So as you approach 0 from the right, it'd be going to infinity. So we have a form of infinity over infinity. This is equivalent. It doesn't matter if it's positive or negative infinity as long as you have an infinity over infinity. Okay. Now that I have this form, I can go ahead and take my derivative using LHOP. Take the derivative of the top, take the derivative of the bottom. Derivative of the top is 1 over x. Derivative of the bottom, negative x to negative second. Now this is one where we got multiple fractions, so we're going to rewrite. I'd have 1 over x, then I got negative 1 over x squared. Multiply by its reciprocal. So now I have my limit as x approaches 0 from the right. This all cancels out. This would give me negative 5x squared over x, negative x. If I plug in 0, I'd have negative 0. No such thing as negative 0. It's just 0. So there is example 6. And then our last example for today. We got secant and tangent as pi over 2 approaches from the left. So tangent really does matter. There is an asymptote at pi over 2. Okay, for that one. But let's talk about our unit circle first. Here it is. We're looking at pi over 2. My ordered pair here is 0, 1. So to find secant of pi over 2. Remember, secant is really 1 over your cosine value. What's my cosine value here? 0. 1 over 0 is infinity. So we think about 1 over 0. And then tangent at pi over 2. Tangent sine over cosine. So my sine value is 1. My cosine value is 0. So that is infinity. So I have an infinity minus infinity. So what our goal is to rewrite by getting a common denominator. Right now I don't have fractions, but I can rewrite my trig functions so that that comes into play. So we have x approaches pi over 2 from the left. Secant is really 1 over cosine minus tangent, which is sine over cosine. That's nice. I don't even have to do any work. They already have a common denominator, so I'm going to put my numerators together. So I'd have 1 minus sine of x all over cosine of x. And now if I plug it in, 1 minus sine of pi over 2. Well, sine right here is 1 all over cosine of pi over 2 is 0. So this gives me the form 0 over 0. Now that I have that form, now I can use the Hopital's rule. I can only use the Hopital's rule once I have 0 over 0, infinity over infinity. Okay, so now I'm going to go and LHOP. Limit as x approaches pi over 2 from the left. Derivative of 1 is 0. The derivative of negative sine is negative cosine. The derivative of cosine is negative sine. Negative over negative, you can think about as positive. Then I always try and plug it in. Cosine at pi over 2 is 0. Sine at pi over 2 is 1. Can you do 0 divided by 1? Yes. And your final answer is 0. All right. That is it for our L'Hopital rules notes for today. Here is your assignment. Okay, so please go ahead and work on that, and I will see you later.